Imagine the universe speaks in two secret dialects, one that measures change and one that sums up its history. These are the languages of differentiation and integration. Together they form calculus, the mathematics of reality itself. But what if I told you that every curve, every motion, and every flicker of light can be broken down into infinitely small moments of change? Well, that is differentiation, the math of capturing the right now. But here's the thing, the reason most of high school students and even college students never really get to enjoy this beauty is because they are stopped at the door by two intimidating symbols, the mysterious little d and that stretched out as letter that stands for integrals. Once you strip away that mystery and just explain what they actually mean in everyday terms, well, that fear is gone. These two interesting symbols, the d and the integral sign, they are the key symbols that are used in calculus, and they are d. We can define it as a little amount of or little bits of. So whenever you see dx, then it means a little amount of x. The stretch out s here, which we can read it as integral and means sum of. And when you see or read integrals of dx, then it means all the sum of the small amounts of x. You might think, why not just add up all the little dx's and call it a day? Well, here is the thing. Dx is just a tiny slice. It doesn't carry any value on its own unless it is paired with something else like a function. That is where the integral comes in. It doesn't just add up dx, it's add up all the little f x dx pieces, which means you're actually summing the values of the function over those tiny intervals. It is like calculating the total area under a curve, not just counting how many slices you have. But one important note I would like to highlight here is why dx matters. Even though dx is very small, it still matters when you multiply it by x, like in x times dx, or square x first, then multiplied by dx, like x squared times dx. These are called first order small quantities. They are small, but not so that small you can ignore them. However, when you multiply dx times dx, you get something even smaller. That is a second order small quantity. And in many cases, we can ignore those because they are really tiny compared to everything else. Example here, why we often ignore dx squared. Let's say dx equal 1 over 60 of x. So 2x times dx become 2 over 60 of x squared. So dx squared becomes 1 over 3,600 of x squared. That's last number is way smaller, like this tiny square here for dx. So it is often safe to ignore it. Dx is small but important. Dx times dx is super smaller and often not worth keeping. But in order to be more practical and answer the question, which is the title of this video, why we differentiate, let us consider a hypothetical position function of an arrow in motion defined as st equal -2 times t cubed plus 15 t squared plus 10t, where the coefficients reflect an initial velocity and gradual slowing due to air resistance. Well, this function is actually constructed for educational demonstration of differentiation in motion. So anyways, as the arrow flies, its speed decreases due to air resistance. Why do we differentiate? Because we want to know or understand how things change at the specific moments, not just overall. An anchor shoots an arrow, it starts fast but slows down because of air resistance. You're interested in questions like, how fast is it moving right now, say 2 seconds after release? Or how quickly is the speed decreasing? To answer these questions, we need to know how velocity and acceleration change over time. And that's where differentiation comes in. Well, this equation shows how far the arrow has traveled after time t, considering a resistance slows it down. So here, if we differentiated this equation here, we get something like negative 6t squared plus 30t plus 10. This gives us the arrow's velocity at any moment. So if we also differentiated this second equation, we get something like negative 12t plus 30, which is for acceleration. So when we differentiated first, we got the velocity equation. When we differentiated for the second time, we got the acceleration equation. Let us plug in some values. Let's say we want to know the velocity at the first 2 seconds. So the velocity will be 46 meters per second when we plug it in the main velocity equation. If we differentiated velocity, or let's say we differentiated velocity and get acceleration, which its equation equals at equal negative 12t plus 30. Let us plug in some values here into this equation. At time equal 2 seconds, the result will be 60 meters per second squared. And at time equal 2.5 seconds, we find the arrow's rate of velocity or acceleration. It's equal 0 meter per second squared. And at third second after it has been launched, minus 6 meter per second squared. So what does this tells us? Well, differentiation let us break down the change into specific time intervals. The first derivative gave us the velocity change over time. The second derivative gave us how acceleration change. In other words, how fast the velocity itself is changing. Even though we didn't explicitly model a resistance as a variable, the fact that both velocity and acceleration are changing over time shows it is effect. That's the power of differentiation. Let us track motion and change with precision. Remember how we broke every motion into tiny bits to see exactly what's happening right now. That's differentiation. The first derivative gave us velocity and the second gave us acceleration. Even showing air resistance at work, differentiation is literally the math of instant change. In part 2, we will flip that idea. Instead of slicing, we will start adding up with integrals. If you found this helpful, please smash the like button, subscribe, and click the bell so you don't miss the next video. Thank you for watching.